Welcome back, viewers. And today we are going to cover a very interesting topic, and that is engine efficiency. Okay. We'll look at some of the elements of efficiency and how can we increase it. So let's get started. So as you remember, this is a schematic of a gas turbine engine that I have talked earlier, as well as Professor Hoekstra has talked about earlier. Yeah. And when we look at the engine in a bit more detail, so it is like a thermodynamic process, right? So like other heat engines, including an internal combustion engine, a Stirling engine, and Rankine cycle, and so on and so forth. So Brayton cycle is also a thermodynamic cycle, which means that it has to have a heat source, right? Any thermodynamic cycle will have to have a heat source, and that heat source is supposed to be at a higher temperature. Yeah. So the engine will take heat from a higher temperature, and then it will convert a part of that heat into work. And in the process of doing so, it will reject part of the heat to a cold reservoir. Yeah? And certainly, the more the amount of heat that is converted into work, the more efficient an engine is. Yeah? But as we know from the second law of thermodynamics and from Carnot's efficiency, is that there are several limits to this ideal efficiency that we can achieve. So when we talk about a gas turbine engine, for example, that is used in civil aviation, then what you see is that there are several processes from a thermodynamic point of view that have to be taken into account before we get the thrust. So there is a fuel on board of an aircraft, then that is converted into heat in the combustion chamber. In the engine, that heat is then converted into work. That work is then given to the propulsor. That propulsor then generates the thrust. And when you look at all these processes, then each process would have its own associated losses. So for the sake of simplicity, you can see here the various steps that are involved. And the last step, that is the power that is given to the propulsor and the thrust that it generates, that is what we call as propulsive efficiency. And the other ones, what we call as thermal efficiency, because that is mainly a function of the thermodynamic efficiency. Yeah. When we talk about a different kind of engine, say for example an electrical propulsion system, then we directly take the onboard energy, which is in the form of batteries, and give it to a propulsor. Yeah. And so then that we can bypass some of the intermediate steps that is there in a heat engine. And that is why when you look at an electrical propulsion system, from an efficiency point of view, it is more efficient as compared to a gas turbine engine or other heat engines. So when we talk about a thermodynamic cycle, certainly when you look at an ideal cycle, Brayton cycle, then it's the efficiency is a function of the pressure ratio. And for a real cycle, it is also a function of the temperature ratio, like other thermodynamic cycles. And the propulsive efficiency, as you have already learned from the lectures of Professor Hoekstra, that is a function of the difference between the jet velocity and the ambient velocity. So to increase the propulsive efficiency, a turbofan engine, which has the capacity to accelerate a large mass flow rate to a small extent, that is more efficient from a propulsive efficiency point of view as compared to a turbojet. And that is why turbofan engines are used in civil aviation. And over the period of time, these turbofan engines seem to be becoming larger and larger, and that is because the bypass ratio is increasing. The bypass ratio is the ratio of the total mass flow rate that is going through the engine inlet as compared to the mass flow rate that is going through the core of the engine. So the core of the engine is becoming smaller, but the fan of the engine is becoming larger. And that is why the propulsive efficiency of these engines is increasing. A turboprop is an example where the bypass ratio is really very high, much higher than turbofan engines. And that is why it is unshrouded. The air, a large amount of air, is accelerated to a small extent. This is the reason why turboprops have high propulsive efficiency at low Mach number flight regimes. But of course, when you go transonic, then turboprops have the problem that the tip losses are increased significantly because of the shock waves and so on and so forth. So turboprops are excellent propulsion systems for low Mach number flights. This is an example of a turbofan engine that we have in our lab, This was donated to us by KLM Engineering Services. This is a CF6 engine, and that was used on MD-11 aircraft. So to summarize what has happened in terms of engine efficiency, then you see that the pressure ratio has gone up. That is what we call as overall pressure ratio. So the pressure ratio at the inlet of the engine as compared to the end of the compressor. Then the turbine inlet temperature, that's the maximum temperature of the cycle, that has gone up. The bypass ratio, which is the ratio of the mass flow rate of the engine as compared to the core, that has gone up. And certainly what has also changed a lot is the combustion technology. And now the combustion technology can burn fuel without producing much soot and NOx. So let's take a look at each of these developments more closely. So what you see here on the slide is the development trend in the overall pressure ratio over the last several decades. And what you see is that the pressure ratio has been increasing steadily. So today, some of the modern engines have a pressure ratio of more than 50. And that means that the pressure at the end of the compressor or the beginning of the combustion chamber is 50 times as compared to the pressure of the air in the ambient. Yeah, that is quite a lot. And certainly this pressure ratio will increase further in the coming years. And it is very challenging as to how we increase this pressure. This has a significant effect on the efficiency of the engine. The other parameter is certainly the turbine inlet temperature. And what you see here is that the turbine inlet temperature is actually much higher than the melting point of the material that is used to make the turbines. And this feat is achieved only because of the sophisticated cooling mechanism that is used to cool the turbine blades. Otherwise, it would not have been possible to operate a material much above its operating limits. The other one parameter that was very important, as we looked earlier, was the bypass ratio. On this chart, what you see is the increase in the bypass ratio of the engines over the last several decades. And again, you see that the bypass ratio has been steadily increasing, thereby increasing the propulsive efficiency and reducing the fuel consumption of the engine. And today, some of the latest engines have a bypass ratio of around 12 plus, and in the years to come, this might increase to 15, 16, and so on, unless and until we have to see where is the optimum in terms of the drag that is created by the shroud in comparison to the benefits that we get by increasing the bypass ratio. This chart below shows you some of these trends. So on the left-hand side, what you see is thermal efficiency. On the right-hand side, what you would see is propulsive efficiency. Certainly, engines have increased both. And that's what you would see in these circles. So these circles are an indication of how engines have evolved. They have increased the propulsive efficiency because of the increase in bypass ratio. They have increased the thermal efficiency because of the increase in the pressure ratio and the temperature ratio and the component efficiencies. Right? But there are certain limits. And these limits are basically dictated by the NOx emission, because NOx emission typically increases with temperature. The amount of fuel that can be burnt in an engine, so the stoichiometric ratio of combustion, and the maximum propulsive efficiency that we could get from an engine in a realistic case. So as you see that we still have quite some way to achieve to these limits. And this is what will keep all the aviation engineers busy for a long time to come. Thanks for watching.